So at this point, I'd like to go ahead and give you a little demonstration on how to go about tackling these types of crashes. Let's go ahead and start out with a Stop 9E, which as you know is a user mode health monitor bug check. We'll then take a look at a Stop 133, which is a DPC watchdog violation. And we'll finish up with a Stop FFFE, which is a driver-defined bug check. So here we are. Let's go ahead and bring up the debugger, and we'll run it in administrative mode and go ahead and open up our first crash dump. I've got it selected here for a memory dump, and as you can see, it is a Stop 9E bug check that we just talked about. It's got the 4 different parameters. We can see parameter 1 is a process ID. Here's the actual timeout value, and then we don't see either parameter 3 or 4. So we can speculate that this is a 2008 system, and that happens to be the particular build number. So it is a Windows 7 kernel, which is 2008 R2 SP1. So, as I've recommended in the past, I highly encourage you to look at the online help, in particular the bug check code reference table, to look up how to go about troubleshooting this crash. But since we just reviewed some information on that, we'll just go ahead and go straight forward with this. As you can see, the debugger has already said that it was probably caused by the RHS process, so we can pretty safely conclude that this is the process ID of the RHS process. But let's go ahead and take a look at a few things before then. We know this is the timeout value, so let's go ahead and take a look at that value. If we do a question mark of 4 Baker 0, it tells us that it is decimal 1200 seconds. So we can do a little math on that by doing essentially 0n 1200 divided by 0n, which means decimal, divided by 60 seconds tells us that 20 minutes is the timeout value that we have exceeded. So we know that this is one of those scenarios where the RHS process hasn't responded or terminated within 20 minutes, and we need to investigate why. Now, we can look at the current thread that was executing at the time of the crash, but this really doesn't have too much bearing on the crash itself. As you can see here, something called reporting services service was running at the time, and we could take a look at its stack over on the far right. You can see it was just executing a system service. It did some sort of set event followed by an interrupt, a DPC type interrupt, and it tried to retire the various DPCs, and then it noticed that it had expired a timer, and that's when the NetFT watchdog timer got involved, and that's the driver that actually crashed the system, as you can see at the top, a KE bug check EX. So that was the current thread that was running at the time the system crashed, but it doesn't really have a bearing on why it crashed. So the thing we want to look at next is perhaps bang running -IT. This will show us all the different threads that were out there running at the time of the system crash. So let's let that go ahead and execute. As you can see, there are 12 CPUs because it's 0 based. So let's go ahead and scroll back up and take a look at what was running on the different CPUs at the time. So on CPU 0, we can see that that was indeed the process that bug checked the system that we just took a look at that thread. On CPU 1, we can see that the system is running the idle loop. So it's just an idle thread running. The same with CPU 2 was the idle thread running, CPU 3, CPU 4, 5, 6, 7, 8, 9, 10, and 11. So all the CPUs except CPU 0 was idle. So that may be just trying to get your bearing on what all was running on the system at the time. So if we do the .bug check command, it tells us the different parameters. And as we know, the first parameter is the process that failed the health timeout. So what we'll do is a bang process command to take a look at that particular process that was called out in the bug check. Now, a lot of information is scrolling by, so we're going to go back up and take a look at all this. So here we go. We'll just page up to where the command started. As you can see, a lot of information. So here we are. I did the bang process command, and it tells us that it is indeed the RHS process. Now, as you may know, a process is composed of one or more threads. So that's what it's showing us right now, are the different threads that were running at the time. So here's the first thread. It was executing, obviously still the RHS.exe image. And you can see its stack pattern. And this is important. As we take a look at this stack pattern, you can see it was doing some sort of system service, and then it tried to deliver an APC at this point, and it essentially started waiting for a single event to occur. Now, I point this out because even though the RHS has many threads, you'll soon see that most of them are doing the identical thing. So as I scroll through the different threads, you can see that here's the next thread, and it's doing essentially the same thing. It's delivering an APC, and then it's waiting. If I look at the next thread, it's doing the same thing, delivering an APC and then waiting. So I'm going to scroll through here looking at all the different threads until I find one that is significantly different. Here you get a few noise type errors just because a page wasn't present in the dump file. But as we continue to scroll on, here this one was a little bit different. It was executing in the Win32k subsystem, and then it was indeed waiting for a single event itself. But as we continue to scroll by all these various threads, here's another one doing the deliver APC and then waiting. And as you'll see, I keep scrolling by more and more threads, and then they're doing primarily the same thing. But now we finally get to a different thread, and it's doing substantially different stuff. So let's take a moment to review it. Once again, it's obviously part of the RHS process. It's got two I/O request packets outstanding, as you can see. Here's one and there's the other. This means that this thread was waiting for an I/O to complete, and it wasn't completing for some reason. So let's take a look at the stack. As we can see, the stack is a pretty long stack. We'll go down to the bottom where it's executing a system service. It then does an I/O control file. It's trying to do some sort of control with a device. Then the NTFS driver gets involved, and you can see it's trying to actually dismount a volume for whatever reason. It's trying to do various things like close a handle, and then the CLFS driver gets involved. That's the common logging file system, which is used by the cluster service to update quorum information. So that driver continued to run doing all sorts of stuff before it was finally asked to wait. So that could be a big clue right there, is this thread appeared to be dismounting a volume, shutting down a volume and dismounting it, and the common logging facility was trying to do some updating to the quorum device. So let's continue to look at the various threads. There's another one right here, as a matter of fact. The next following thread was also trying to do some sort of I/O request, and the partition manager driver got involved, where it actually tried to do an I/O read partition table. So a variety of things are occurring with these two threads, and this thread also had a couple of outstanding I/O request packets, so we'll want to take a look at those. So those are the two threads I'm interested in. The rest happen to be very much the same thing, where we've got the APC being delivered and waiting. So what I'd like to do at this point is go take a look at those two threads of interest. So here we are at the first one, and I want to take a look at these I/O request packets. So what I'm going to do is essentially the command bang IRP giving it the address of that IO request packet. I'm going to put a semicolon and then do another bang IRP and take a look at the other one too. So this is how you essentially can stream multiple debugger commands together. So as I issue this command, it gives us lots of information about these IO requests that were generated. So here we have an IRP that was, as we know, dealing with the common logging file system, and it has essentially a device ID right there. And we could take a look at that device ID and get a bit more information about it. Namely, we'll go bang dev stack, and it tells us information such as the various drivers involved. Now that was one of the device IDs. Let's go take a look at the other one. It's right here. So let's go ahead and take a look at that dev stack, see if it gives us just a little bit more information. It was part of the CLF driver. So let's go ahead and take a look at those other two IO request packets from that other thread we took a look at. So here we are looking at, here we are, the partition manager driver. So let's take a look at these two IO request packets. I'm going to do a bang IRP command, and then we'll tack on another IRP command to take a look at this other one. As we issue this command, we see the various informations about the partition manager driver. So let's go ahead and take a look at these device stacks here. We can take a look at this first one and see what other devices are associated with this. And we can actually take a look at that second one too. Bang dev stack right here. By getting the device ID, we could see the device stack, and lo and behold, we could see the device that we're dealing with is DR9, or the MPIO Disk 6. It tells us that it's actually part of a left-hand storage and that it's an iSCSI disk. So for whatever reason, we've got several stuck IO requests that have been executing, and we can actually see how long they've been executing by looking at the thread. So as I look at the thread here, we've got a time period of 24 minutes and 58 seconds. So it's almost been waiting 25 minutes. 5 minutes for the deadlock timeout to occur, and another 20 minutes for the RHS process to not respond or terminate properly. And that's why the system ultimately crashed. So looking at the system event log, it was determined that the actual iSCSI devices had gone offline, and that was because the system had encountered network problems where the actual iSCSI server had been forced to terminate. So in summary, we encountered this crash because we lost access to essentially the disk because it was an iSCSI based disk, and we could see that through these outstanding IO request packets that weren't completing in as much time as 25 minutes. So when the cluster saw this, that the RHS was not responding in a timely fashion, it ultimately crashed the system with a stop 9E bug check.